Hello, I welcome you to a new video segment on aesthetic leg lengthening. Today we have Professor Augustin Betz with us, and we would like to provide you with at least some structure regarding the types of implants used for leg lengthening. First, I would like to briefly touch on the basic principles of distraction osteogenesis. This is important just to understand to what extent which systems have made progress, or which systems make sense or make less sense, and are used for leg lengthening. When we talk about leg lengthening, we talk about the basic principle of the Ilizarov. He developed it. Discovered, however you want to put it. And that means nothing other than that you have a bone that you cut through. You have two bone ends here. And then he discovered that between these two bone ends, basically, new bone tissue forms. The whole thing is called kalos. And now it is like this. If you check these two bone ends, pull them apart, move them apart, then it is not the case that they always have solid bone, and the solid bone breaks. And then they have solid bones again, and these break again. Instead, they have this kalos as a more chewing gum-like structure, and they can pull this kalos, I'll call it chewing gum, apart at a certain defined speed. That means if you basically pull too slowly, it may already be ossified. But if you pull too quickly, then this gum can tear apart, and you develop what's called a pseudarthrosis, which means a structure where the bone doesn't heal. So, now we have this Ilizarov principle, and apply this Ilizarov principle to our legs. That means we want to lengthen the legs. Accordingly, we inevitably have to cut through the bone. It doesn't work quite differently. And we need to pull these two fracture ends, that is, these two bone ends, apart at a defined speed. The problem here is not the defined speed and the pulling apart, but the problem is stabilization. Because these two ends of the bone must not end up like this. The three-dimensional direction during the pulling apart must be maintained. Otherwise, you either have a step in this bone, or you tend to have bow legs or knock knees, or you basically have a misalignment, and that can, or rather that must be prevented. So now let's move on to the systems that are supposed to ensure exactly this. Ideally, the defined speed of distraction, which means pulling the callus apart at this specific speed, 0.1, 0.2. But also to ensure stability while pulling the callus apart. And now there are two ways to ensure stability. We have one way to ensure stability is through an external fixator. I have these magnetic cards here, and I'm just going to put them here. So we have an external fixator. What is an external fixator? An external fixator, the basic principle of the ring fixator, I'll just take it here and show it to you. That means you have a structure outside the body that is stabilized, which ensures that this does not happen. This is ensured in 3 dimensions by many splints that are screwed into the bone. And this ring, it can also be a 3/4 ring, basically stabilizes the bone. That would be a ring fixator. The problem with the ring fixator is, as you can see, it's relatively bulky. You have a whole bunch of splints that not only go through the bone to stabilize it in 3-dimensional directions, but you also have these splints that go through the skin. And that is the main problem with all so-called external fixators, that is, with all devices, structures, whatever, that are intended to carry out distraction, that if external fixator, having a connection between the bone and the skin surface, and thus having the risk that germs can enter. So, we then have our internal fixators. The second group is you can also stabilize the whole thing. Not through external force application, but we can also stabilize the whole thing through internal force application. That means here we have a thigh bone, for example. Now we don't have an apparatus around the outside to stabilize everything, but we have a structure in the medullary cavity that is supposed to stabilize the area. Basically, The principle here is to ensure that a so-called dislocation, a shift of the fracture ends or bone ends, is avoided with a so-called internal fixator. This is nothing other than a so-called nail system that is inserted into the bone, blocked by two screws, one at the top and one at the bottom, and thus stabilizes the bone. This nail system, you can now distinguish, especially in the area of distraction, between the mechanism by which this nail system performs the distraction. That means we can distinguish our nails, the internal fixators, into purely mechanical nails. These purely mechanical nails have nothing but a ratchet system. And through this ratchet system, the nail is pushed apart. That means the process of distraction in mechanical nails is really achieved by a thread that is connected to a micro ratchet system. I'm just demonstrating that with this system here, we have inside the inside of the nail, that's the casing of the nail. I've already explained this in a bit more detail in another video sequence. And we have a counter-rotating gear system, the mechanical mechanism that guides this thread through the casing, so to speak. That would be the basic principle of the original Albesian nail. This micro-ratchet system. And from this Albesian nail, several other nails have developed, including the Betz drilling nail. And, among others, the Geschehennagel. Both, or rather, all three are based on this micro-ratchet system. It's also worth mentioning the mechanical nails. The ESKD, it has now been taken off the market. Very simple, because the control over the feed mechanism was correspondingly poor. That means either he extended it at an uncontrollable speed, or it didn't extend at all, because those ends were already ossified. That means the control of the feed was very poor with this one. And for that reason, it has practically been taken off the market. The next group of internal fixators are electric nails. Electric nails are useful. To that, we mainly mention the Fitbone nail. With the electric nails, it works like this. You have the nail. Inside the nail, there's a chamber where the motor is located. This motor then drives a screw spindle. The energy for the motor, or rather the threaded spindle, comes via an induction patch field that is sunk under the skin and is connected from the outside to a so-called pillbox. It's coupled. That means with the purely electric things, especially with the Fitbone, the drive mechanism is located in the nail. And different chambers that are then separated from the body fluid. This is very important for later when we get to the individual advantages and disadvantages. So, now we have our third group, our magnetic nails, exactly. Magnetic nails, workhorse. Here, the precise lag. With the precise nail, it is like this. You have the drive mechanism, which is inside the nail, basically it's purely magnetic. And you have a module that you place outside of the body to drive, initiate, or stop this magnetic feed mechanism, accordingly to stop it. So, now we've talked about the nails. A rough overview. We have purely mechanical nails. We have electrical nails and we have magnetic nails. Then we have the extension mechanisms, which are derived from an external, that is, outer system. And now we have a special group. We have the combination of an external and an internal system. I'll go over the external fixator again. We either have a ring fixator, which manages to provide stabilization in all three planes. Another variant of the external fixator is the unilateral fixator. The unilateral fixator takes a bit of a special position, especially when we talk about a so-called hybrid, namely LON. That means lengthening over nail, lengthening over a nail. Then basically nothing else happens than that you have a rigid, solid nail. It would look like this. This rigid, solid nail does not have a system integrated for extension. That means it's nothing other than a complete nail, which is also used in accidents. And to create an extension mechanism, basically, this fixator is used. And this fixator is then additionally inserted alongside the nail and permanently, with screws from the outside, so to speak, turned further to carry out the distraction mechanism. Just using a unilateral fixator that is basically stabilizing from the outside with a unilateral fixator would be nothing more than a system on one side that is secured to the bone with screws, which is practically not possible. And why is it not possible? That is simply based on the principle that you cannot create three-dimensional stability with it. That means if you attach a unilateral fixator here and try to pull the bone apart with this unilateral fixator without internal stabilization, then it will inevitably lead to a shift in some dimension or direction. In the worst case, the whole system bends like this, that they either develop a crazy bow leg in the lower leg area, or even in the thigh area, the bending can't be held at all. And for that reason, this LON originates. This basically means that you cannot take an external fixator. That means you have this monolateral system and add an internal nail to increase stability. To ensure stability during distraction, that's basically it. Everything that describes LON here. LON is not a nail that has an integrated advancement mechanism. It's not. Rather, it's simply a completely normal solid nail. And this solid nail stabilizes the bone. Then, in addition, an external fixator is also introduced to highlight the distraction mechanism. That's the difference between internal fixators, external fixators, and the hybrid, so to speak, the LON system.